Hi everyone, this is Everything is Relative. My name is Mr. K, and today we'll be doing a crash course on the topic of motion in a circle for Cambridge A-Level Physics subject code 9702. Now this is not going to deal with the course in its entirety, but it will be a summary of the course, the important definitions, equations, concepts, etc. This will go hand in hand with a mind map, for example, that you would do to prepare for studying for a test, exam, and so on, or just to simply revise the section. We will create another video at some point answering more difficult, in-depth questions, maybe from past exams. So, on the topic of motion in a circle, it is a fairly short topic, but can get a little bit complicated, especially with definitions. And one of the first definitions we come across is that of a radian. So we may have seen a radian in mathematics, but we may also have not fully understood the topic. So a radian is simply a measure of an angle. One radian is, I'm going to type out the definition as you would see it in the textbook, defined as the angle subtended at the center of a circle by an arc equal in length to the radius of the circle. So the word subtend simply means to create. So it's the angle created by two lines at the point at which they meet. And so this is the angle subtended at the center of a circle by an arc equal in length to the radius of that circle. Quite a bit to digest. So what does this mean? Well, as a definition, it's all well and good, but it's important that we know what this physically looks like. So let's try and put this definition into perspective. So if we have a circle and we consider an arc, which is a distance along the circumference of the circle, we'll call this distance S. This is the arc of the circle S. Then if I draw the center point and a radius, remember radius is any line from the center to the surface of the circle, and I do that for either end of this arc S, the angle subtended, or the angle simply created, we'll call theta. And so what this definition says is that if the arc length is equal to the radius of the circle, if these two distances along the circumference of the circle and the radius are equal, then this angle is equal to 1 radian, or the symbol for radians is rad. And so that's a definition of an angle theta. That's what a radian is. So it's simply another way of measuring angles. It's in place of using degrees. So what this means is that theta in radians is the arc length divided by the radius of the circle. So let's take a complete circle. So we're doing a little bit of mathematics before we can apply the relevant physics. So if I have a complete circle, my number of radians, if I were to take a walk around this entire circle, where my arc length S was now the circumference of the circle, S would be 2 pi r. So theta would be 2 pi r divided by r. Guess what? The r's cancel. All I'm left with is 2 pi. That's good, because now I know that going around the circle, across the entire circumference, is 2 pi radians, and I know that if I walk around the entire circle and begin and end where I began, I've covered 360 degrees. So 2 pi radians is 360 degrees, meaning a single radian. Remember, these are just two units of measurement, so I can always convert between them. A single radian is 360 degrees divided by 2 pi. Put this into my calculator, knowing what pi is, and I get this to be 57.3 degrees. Obviously, there are more decimal points, but to three significant figures, that's 1 radian. It's 57.3 degrees. It's a lot easier to say 1 radian than it is to say 57.3 degrees. And so our unit of measure for angles at least for now, will be the radian. And so we can define another quantity based on this. We can define something called the angular speed. So this might be a new quantity even if the radian wasn't. So what is an angular speed? Well, we know the speed in general is the amount of meters I've covered per unit time. So my regular speed v is displacement divided by time, okay? But my angular speed is going to be given the Greek letter omega. Looks like a small w. And omega is the number of thetas I cover per unit time. The amount of thetas, or the angle by which I walk across the circumference of the circle per unit time. And so what this means is my angular displacement, when you use square brackets to indicate units, will be measured, my unit of measurement for omega will be the number of radians I cover every second, so rad per second. And so we have to remember that angular speed is delta theta by delta t. My change in angular displacement, which is simply what delta theta is, angular displacement over my change in time. Sort of makes sense. If I cover a greater number of thetas every second, I'm traveling faster around the circumference of the circle. And so the unit of measurement for omega is radians per second. Now, we aren't going to show all of the derivations, and the mathematics itself is not that complicated, but with a little math, we show that the linear velocity v is equal to the radius of the circle times the angular velocity, or the angular speed omega. And so what does this actually mean? Let's draw another circle. Let's label this again, shall we? And so if I am moving around the circumference of the circle with an angular speed omega, the circle itself has a radius r, then if I draw myself from the top view, when I'm at the edge of the circle, my linear velocity, or my speed, simply is v, and it is tangent to the circle. If I walk a little bit more, I'm still walking in a circle, but at that specific point, I have a velocity that is again tangent to the circle. So at any point in the circle, my velocity is always pointing tangent to the circle. You notice that it's also pointing perpendicular to the radius if I were to draw the radius at that point, which is a very important point that we'll see the importance of later on. And so my angular speed, omega, if you remember from waves, the concept is exactly the same. It's 2 pi divided by t. Now, uppercase T here is the period. It's the time it takes me to walk one complete cycle of this circular path. The time it takes for one complete oscillation, if you will, if you remember the topic of oscillations. And so omega is 2 pi over t, or 2 pi over f, where frequency is the number of revolutions, or the number of radians I'm covering every second. So how many revolutions am I doing every second around the circle? And so this is this analogy here with the topic of waves and oscillations. And so what I can see here is this velocity points in different directions. So if I consider this first point to be A and then the second point to be B, the velocity is constantly changing. But wait, we remember something about this. If velocity is changing, but remember, velocity is changing maybe because direction is changing, not because speed is changing. So maybe it's important that we write that down. So direction is changing, and I'm not walking any faster, nor am I walking any slower. So my speed, the scalar, is remaining the same, but the vector is indeed changing. At A it's to the left, at B it's completely downward. And so if velocity is changing, we know what that means. That means I'm accelerating. So the object moving in a circle is undergoing acceleration. Not because the speed is changing, but because the direction is changing. So acceleration can occur even if your speed is remaining constant, which doesn't seem as the most obvious thing, but it's possible. You could be accelerating without your speed changing, and that's the topic of oscillations. Okay, so if I consider the object moving in a circle, we haven't yet considered why the object's moving in a circle or what type of circle it is, but it is moving in a circular path. It could be the moon orbiting the Earth or the Earth orbiting the sun. It could be a ball in the end of a string. It turns out all of these motions are at least mathematically identical. So what's happening is if I draw a little point to represent the center of the circle, the acceleration always points towards the center of the circle. But wait, let's do this again. Let's assume that I'm moving anti-clockwise. In both cases, I'm moving anti-clockwise, so my angular speed, my omega, is anti-clockwise. Again, my velocity is tangent to the circle, but remember, Newton's second law doesn't simply state that F is equal to ma. It also states that the direction of F and the direction of A are the same. And so from Newton's second law, if I have an acceleration that's pointing towards the center of the circle, I also have a force pointing towards the center of the circle. And so my force and acceleration are both pointing towards the center of the circular path through which the object is moving. And so I have something called centripetal acceleration. And so the idea is that whenever you have circular motion, we use the word centripetal to identify this. And centripetal means center seeking. So seeking the center of a circle is what the acceleration and the force are doing. They're pointing towards the center. And so we're going to do some more mathemagic. With a little bit more mathemagic, we get the acceleration to be v squared over r. But wait, we had an expression for v. We said v was r times omega. So I'll write that as r times omega all squared over r. And so this becomes r omega squared. So now I have an expression for the acceleration as a function of the radius and the angular velocity or the angular speed. And so it doesn't take much more manipulation from here to see that I can label a quantity called the centripetal force. The centripetal force is the force that is causing the circular motion. It is force that's pulling the object towards the center of the circular path. Newton's second law in magnitude tells us F is equal to ma. That means I simply take the equation above and I multiply it by m. And so I get mv squared over r, or in terms of the angular speed, mr omega squared. So you can see that this force depends obviously on the mass, but also on the radius of the circular path and the angular speed with which the object is moving. Note that the speed here must be constant, must be a constant v, and the force needs to be constant as well towards the center of the circle. So for centripetal motion to occur, we must have a constant force, a constant speed. Velocity won't be constant, but the speed certainly will. And we need that the force and the speed, or the force and the motion need to be not parallel, but perpendicular to each other. That's the symbol for perpendicular. So force and motion must be perpendicular, meaning v, the direction of the velocity at any point, and the force must be at 90 degrees. If we satisfy these conditions, if v is constant, f is constant, and they are perpendicular, guess what? We have circular motion. We have centripetal motion, or centripetal, depending on how you want to pronounce it. And so now we have our conditions for centripetal motion to occur. Remember, if the force is not constant or the speed is not constant, then we may have a curved path, but we don't have completely circular motion. Curved paths are great. Circular motion is even better because it's easier to do the relevant mathematics and study these scenarios. And they happen in nature all the time. The planets orbiting the sun, the moon orbiting planets, etc. Good example of these. Motion is not completely circular, but they could be assumed to be circular for very basic calculations. What's important to remember is that this centripetal force is not a specific type of force. It's not like the gravitational force or the strong nuclear force, for example. It is simply the resultant force of all the forces that cause circular motion. So if an object is moving in a circle, we consider all the forces acting on it. We take the resultant of those forces. That resultant is then labeled the centripetal force. So that's for an object undergoing, or I'm going to say in circular motion, to be a bit lazy. Okay, so let's put this into some examples to see where this would apply. So some examples, one of which would be, I'm going to draw the Earth. The Earth moves around the sun. We're going to assume that the path of the Earth is circular about the sun. We know this is not true, but we can assume it to be the truth, at least for estimation purposes. And it has some angular speed omega, if we're looking at it at 2 dimensions from maybe the top down and looking at the plane at which the Earth orbits the sun. So in this case, there's only one force between the Earth and the sun, and that's gravity. And so what this means is that the gravitational force is the centripetal force. And we sometimes denote centripetal force with the subscript c. So we'll use uppercase F for force and little c just to say, well, that's the centripetal force. What happens if I change the scenario? What happens if it's, and you, again, if you're studying this, you would have already seen these kinds of examples, but let's assume this is a ball traveling in vacuum. Let's assume it's doing a horizontal circle. Let's assume there's no gravity. Let's make it a very ideal scenario. The only force acting on this ball is the tension in the string. And so if we attach the string to some fixed point at the center, and the ball moves in a circular path around that fixed point, then it turns out the only force acting on the ball, since we're ignoring gravity and the other forces, is tension. And so the tension is the centripetal force in this case. And so those are some examples. There are other examples. These are just 2 examples of where circular motion can occur. They can occur with any types of force. In this case, tension, and in the first case, the gravitational force. Now let's look at a more complicated example. Let's assume we have a car on a circular banked track. Now the center of the circular bank or circular track is toward the left in this example. If we were to draw the forces acting on this car, we'd first label the weight of the car acting vertically down towards the center of the Earth. We then know there would be a normal reaction force that the track would exert on the car we'll call it R, and this force would be perpendicular to the surface of the track. Now we can resolve this into components, not completely drawn to scale. We'll have a vertical component, and we'll call this RV, and we'll also have a horizontal component as we look at it that will point to the left. We'll call this RH, and if the center of the circle is toward the left, then it is purely the force RH that is responsible for the circular motion and is hence the centripetal force. So the component of the normal reaction force that is pointing towards the center of the circle in this case is the centripetal force, and that's RH. And there are no other forces that contribute to the circular motion. So we took the same example of circular motion and applied it to something a little bit more complicated. We can also apply it to motion in a vertical circle. And so a simple example of a vertical circle would be a circular loop on a track. And so let's assume we have a roller coaster moving through a circular path, or a portion of the track that is circular. And if we were to draw this roller coaster, albeit quite poorly, we'll take one point of the motion where the roller coaster is on the inside of the track but at the top, and another point of the motion where the roller coaster is at the bottom. We'll give this roller coaster, at least the carriage of the roller coaster, a mass m, and at the top we'll assume that its velocity is to the left, which means that it's traveling anti-clockwise within a constant angular speed omega. Again, we're making the assumption that the angular speed is constant. At the bottom, v points to the right, and this circle has a radius r. So this is a vertical circle. So as we look at it, it would be the axis of the circle would be into or out of the page, and so this circle is upright, hence vertical circle. So let's break up this motion into the top part of the track and the bottom part of the track. Now, at the top part, the acceleration of the cart is downward. And so what this means is that the resultant force must be downward. But remember, the resultant force for circular motion is simply the centripetal force. So let me draw a force diagram or a free body diagram for the carriage of the roller coaster. The weight of the roller coaster W points downward, and the normal reaction force that the top of the loop exerts on the cart will also be downward, since the loop is pushing the cart downward. And so what we have is that the resultant force, since it is downward, must be the sum of these two downward forces, the normal reaction force and the weight. And using the equation we derived before, this means that mv squared over r is n plus w. This is a simple example of an application of circular motion if we are talking about a vertical circle. Notice that there is more than one force that can be responsible for centripetal motion. In this case, it's the weight and the normal force, both pushing down on the carriage, which is moving in a circle at constant speed with constant radius, and so the centripetal force is the sum of those two forces. Now let's look at the other part of the motion, which is at the bottom. At the bottom, the center of the circle is above the cart, and so the acceleration and hence the force must both point upward, and so the entire scenario changes. So if we have the acceleration upward, we must have the centripetal force, or the net force upward. Drawing a force diagram on the cart is now slightly different. The weight will still act vertically downward toward the center of the earth, but the reaction force of the track on the cart is now upward. So the track pushes the cart upward with a force N, N being the normal reaction force. Now the centripetal force, like we said, must point upward. So the net force must be in the upward direction, which means that the normal force N must be larger than the weight W. So Fc is N minus W, or simply mv squared over r is N minus W. And so before we said the acceleration is down, in this case the acceleration is up, always pointing towards the center of the circle. And so we created two simple expressions for the centripetal force at different points of this vertical circle. So the last point I want to make in concluding the crash course is that, remember, the centripetal force, we said, is always perpendicular to the velocity. And so what this simply means is that the force, this is the symbol for perpendicular, the force and the motion are always perpendicular. Remember an old definition, that of the work done. Work done is the force multiplied by the distance that the object being moved by the force moves in the direction of the force, r cosine theta. But the force and the motion are always at right angles, which means theta is 90 degrees, and the cosine of 90 degrees is also always 0. So the work done by any centripetal force is always 0, which means that centripetal forces do no work. So I hope you guys enjoyed this crash course. We'll be doing the same for all of the A2 physics topics, and then possibly going back and doing it for AS physics. But again, this is not a full treatment of the entire topic, but simply a guide to help you study and prepare for your exams. Until next time, I'm Mr. K.